Good afternoon, good evening, and good morning. Welcome to today's webinar. I'm Skylar Villasenor, a student volunteer at Nova 77. I will be your moderator today. Today's speakers are Kevin Yang and Yogesh Kumar. They will talk about their winning project, LLOCUST, for the NASA Space Apps Challenge 2020. Kevin and Yogesh, welcome.
Thank you.
Thank you, Skylar. All right, we can jump into the presentation, I guess. Right, can you guys see that fine? All right, sick. So yeah, exactly what Skylar just said. I'm Kevin, and then I'm presented with Yogesh. We both worked on Project Locust, and this was our project that we submitted for NASA Space Apps. And this one project with most likely to have an impact on the world. So I guess before we begin, should probably give a background on both of us. So I'm Kevin. I'm from Boston, Massachusetts. I'm currently a freshman at Newton South High School. And I guess what I do for fun, I hope to become an electrical engineer. So on the bottom left, you can see a PCB that I designed for Hack Club. And then on the bottom right are two initiatives I'm a part of. So the big E is a RevNA, which is a Harvard student-founded initiative where I spearhead their hackathon department, oddly enough. And the bottom right, the bear claw, is combat robotics at UC Berkeley, which is UC Berkeley's BattleBots team. And we plan to compete in BattleBots this summer, actually. So handing it off to Yogesh.
Hi, everyone. I'm Yogesh Kumar. I'm originally from India, and currently I'm in Germany pursuing my master's in computer science. So the owl that you see next to my photo is the university that I study at. It's called the Saarland University, which is in Saarland, Germany. And I'm doing my master's in computer science, as I said, but my major focus is towards deep learning and software development. And the DLR over here stands for Deutsches Zentrum für Luft- und Raumfahrt, which means it's the German Airspace Center. And I'm currently doing my master thesis there. And Kalins over here is the company that I'm currently part-time research associate working in video depth estimation. Back to you.
All right, so I know Ping hosts the Las Vegas Space App, but to all those in the audience who aren't familiar with NASA Space Apps, it's essentially a 48-hour hackathon hosted by NASA that allows participants to solve challenges that NASA are currently facing. It's a great way to meet with people across the world and work collaboratively with them towards solving these challenges. And so on the note of challenges, this year's NASA Space App 2021 had 6 challenges. So they had observe, inform, sustain, create, confront, and connect. And so of these 6 actually, our team was most interested in the inform challenge. And so under the inform challenge, there were 3 subtopics. So a digital history, a carbon footprint, and an automated detection of hazards. And of these 3, our team chose to tackle the automated detection of hazards, mostly because we were a group of machine learning enthusiasts, and we believed that this challenge could best use our skill set. So giving a bit of background about this challenge. So NASA essentially wants us to use satellite data to create a machine learning model that detects and displays specific natural phenomena. So by natural phenomenon, it means anything from weather to locust flakes, I'll talk about in a bit. And then one added criteria to this is that that not only do you have to create a machine learning model, but you also have to display in a way that is user-friendly to people, because NASA not only wants a model, but they actually want the model to be used in the real world, right? So it needs some sort of interface between people that is easy to use. So with this challenge, we brainstormed a few ideas. And so here's an example of a few. So we came up with a fire detector, a hurricane detector, and a Mars dust storm detector. Of these 3, we actually did not choose any of them because for the first 2, for the fire and hurricane detector, they sadly already exist. And quite frankly, they're somewhat generic ideas. We knew that if we wanted to have success in this competition, we would have to pursue something a little bit more novel. So that brings us to the Mars dust storm detector, which is a fairly novel idea. Doing some quick research, there hasn't been much work on this, or any work at all. The problem with this is that since there hasn't been much work on this, there actually lacks sufficient data for pulling this off. And our team didn't want to spend the weekend labeling a data set while we could be doing something much better. So, this kind of left us in a pickle because we started off the week on Monday brainstorming ideas and looking at the challenges. And it was Friday night now, and we had yet to decide on an idea. So it was getting fairly late on Yogesh's end since he's in Europe and I'm on the East Coast. So he started calling it a night. And then I knew that if we woke up tomorrow morning, so on Saturday morning, and we didn't have an idea, we would be completely toast for the competition. So actually, I started procrastinating instead of trying to find an idea. So I was just looking through my news feed, and then I saw a bunch of articles talking about this locust plague that's absolutely ravaging Eastern Africa. And so this got me thinking because in the articles, they talked about these huge swarms, a mile by a mile, 100 mile by 100 mile wide. So think of the size of New Jersey. And they were absolutely decimating um, Kenya. They were eating all the crops. Um, and so this got me thinking, because if these swarms are that large, then you could potentially see them from space, right? Um, and so I guess that's exactly what we tried doing during the hackathon. So our Project Locust, is about this problem, about these locust swarms that are ravaging Eastern Africa, the Southern Arabian Peninsula, in northern India. So to give a quick summary about Project Locust, it's essentially able to identify, predict, and forecast locust swarms in vulnerable areas. And so you can think of Project Locust as both a machine learning model, but also a interactive user-friendly website. And so for the machine learning model, it takes in satellite data from NASA, such as wind, humidity, surface temperatures, and vegetation index, where it's then able to get the risk of a certain area, as well as able to detect whether locusts are present at that area. And so this entire project, I guess, is designed for city officials, farmers, and local businesses, which are the people who are directly affected by locust. So I probably should give a bit of background on locusts since our entire project hinges on them. So if you're familiar with grasshoppers, locusts are fairly similar to them, if not for one key difference, which is that unlike grasshoppers, locusts actually have two forms. They have a solitary phase and a gregarious phase. And so in solitary phase, they are basically grasshoppers. They're green, they bounce around, they're completely harmless. But then when they start breeding in numbers, so when there's a huge collection of locusts in a certain area, they go from the solitary phase, where they're green, into a gregarious phase. And so in this yellow phase, they are extremely harmful and they start swarming together. And a few unique properties of locust and gregarious phase is that they eat their body weight per day. So this might not sound like a lot since locusts are fairly small, about 10 grams. But with an average locust swarm, about 60 million, this number of just one swarm and the amount it can eat in one day is huge. A small swarm can easily eat an entire farm. And so this as I said earlier, they breed, and this gregarious phase is caused by being in numbers. And so they breed near humid and lush areas, which becomes important for our data inputs, which Yogesh will talk about in a bit. And they also congregate near high vegetation, since they need to eat, right? And high vegetation are the plants in which they eat. And then also one unique property about gregarious locusts is that they're extremely lazy, which is a good thing for us because locusts don't actually choose where they want to go. Since they're lazy, they prefer to fly with the wind. So the wind pushes them along, which allows us to forecast where locusts are going, which I'll talk about in a bit. But moving on, I'll hand the mic to Yogesh, which he'll break down our process in making the machine learning. So Yogesh, take it away.
Yeah, thank you, Kevin. So, hi again. I'll be breaking down our whole process of developing this machine learning model and adding the forecasting at the end. So, we divided our tasks into these four things. So, the first one is the data acquisition. This is one of the most challenging, tedious, and time consuming process. And once this was done, we had to convert the data so that it can be used in a usable format to train our models, which is the third step. And at the fourth step was the location forecasting, where we use another data set to help us with that. The next slide. Yeah. So acquiring data. So were not handed any ready-made data set to work with. So what we did was we combined these two websites to generate our own new data set. So the first one is the NASA Earth data, which provides satellite view of the Earth with different spectrums such as soil, moisture, temperature, etc. And the second is the FAO. It stands for Food and Agricultural Organization, which gave us the exact predictions, not predictions, exact data set of all the past locust outbreaks which were done in the past, which were happened in the past 30 years, with the coordinates and the time frame. So we combine these two data sets, knowing that we have the coordinates and the time where this happened, and we have all the features that we want from that those data. So in the world view, this is what the data looks like. So we have the normal output, the elevation, the soil moisture, vegetation index, and the temperature. So after doing a lot of research online about what do these locusts actually depend on, where do they actually breed, so these were the most important factors that came. Actually there were even more, but we had to jot down to these because of lack of data even in this EOD's website. So on the left we can see the normal output as you see in your Google Maps, and but that's not enough because we can't really see them from space, so we had to see other features. So the first one is the elevation. They usually are in the low-lying areas, so a greener pixel would be a better chance of them being there. And similarly the vegetation index, soil temperature, and the moisture. So next part was the data conversion. So here, once we get the data from the NASA server and from the FAO website, we had to develop a cropper which can give us one pixel value given the coordinate. So how we get this value was from the FAO website, we get the exact coordinate and we have a bounding box of which we extract the pixel value and store it as a hex value. So we do this for all the four different features that we have, and we created this whole data set in pandas. Next part was machine learning. So I'll just give a brief introduction about machine learning. It can be divided into two parts. So this is the classical machine learning I'm talking about. So supervised and unsupervised. In supervised, it's like you give the machine a task along with the examples of how the output should look like. So it's like if I give you a dog and cat, you have to say which is dog and which is cat. And in unsupervised, you just give them dogs and cat and you say just figure out something. So it has to cluster all the dogs somewhere and it has to cluster all the cats somewhere altogether. So unsupervised learning can also be subclassed as classification and regression. So classification is considered, as I gave the example for with dogs and cats, it has to classify in either of them. And regression is where we try to predict continuous values such as the price of a house. And clustering, as I already talked, whether you cluster dogs or cats altogether. So that's a really brief introduction. So next we had to choose some model. So we had to either choose from going either to the classification route or the regression route. So the first thing that struck us was classification because it's easy to predict whether there was a locust prediction there at that coordinate and a time, rather than regressing whether where it could be, rather than predicting the coordinates where it could be. So we chose classification instead of regression. So we tried out many models and these two performed the best. So random forest and support vector machines. So I'll again give a small brief introduction about what random forest is and what support vector machine is. So random forest can be considered as a total a lot of decision trees. And what a decision tree is, it's basically you have some data, you give it to a tree, and tree has many nodes. Each node will ask a question to the data, and based on the answer that the data gives, it's either branches left or right, and you keep doing until you hit at the leaf node. And the output of the decision tree is basically whatever you get at the leaf node. So the number of output at the leaf nodes is equal to the number of data that you have in the starting. So, but maybe why the decision tree didn't give us good results was because it was really sensitive to the input data. If you change even a little bit of data, the predictions of decision tree was really changing, far changing. So if we multiply this decision tree as by n, so we have lots of trees, and each tree has those different nodes where they classify, where they branch out left or right. And then if you use the aggregated version of them and we average out the output, that model is really robust. And that's why I think that this model provided a really great result for us. And support vector machine. So I would give a small intuition about how this works. So let's consider we have blue and red dots that we want to separate. So a question to you guys, I'm sure I cannot hear you, but which line do you think would fit this the best? Okay, so I'm gonna say that it's yellow. That's because we are eyeballing it, so we know which line fits it the best. But it's not the green, because right. But the model can also predict green. It's right, but it's not optimal. So how do we make sure that the model outputs this yellow line? That's where the support vector machine comes in. So support vector machine basically produces those support vectors which maximize the margin between uh, from the optimal hyperplane, so that both the classes are separated as far as possible from each other. And this is done by using different kernels. Either you can use the linear kernel or you can use the RBF kernel in case if the data is not linearly separable. So here you see that the data is linearly separable. We can draw a straight line and separate them. But in some cases, the data might not be linearly separable. So you take it to a higher dimension and then separate it by hyperplane. So that's about support vector machine. And this is how our data look like. So we have the FAO data set on the left and NASA data set on the right. So FAO dataset, as I said, gave us the latitude, longitude, and the time, and whether it always gave us where the locust was. So we had to also get another data set where we didn't have any locust prediction, so that we don't have an unbalanced data set, because model needs to know both where it was and where it was not, so that it can learn something nice. So we chose the data from America, and where there were no locust predictions, and from Kenya where there were locust predictions. And for the exact latitude and longitude, we got the NASA data set over here, which has the soil moisture, elevation, temperature, and vegetation index, and the respective hex values, through which are the basically the features which we feed into the model. And the accuracy which we achieved was almost 70% from both models. And once we have the predictions where whether or not there's a locust existence over there, then we can forecast them just by using the NOAA wind map, because as Kevin said, they are really lazy and they would like to just let the wind take them anywhere where they go. So the model just keeps predicting. It's not the model, but it's the data from the NOAA wind map. So the model has to become less predictable as and far it goes away from the real coordinate. That's because no model can be as accurate as so as our weather forecasting system. So a week from now, it might say it's rainy, and after a week, it's really sunny. So we just can't be sure. So this was it. Back to you, Kevin.
All right, so I'm going to give a quick demo about the project. So here's our live website page. So you guys can also visit this. It's on our documentation here, but don't visit it at the moment because it might crash the server because we're hosting it for free. But so I guess the first thing that I can show is what Yogesh was just talking about. So this is real-time data straight out of NOAA, which is the US's, I guess, weather agency. And so they have a global data set from the entire world on wind velocities and wind directions at any point on the Earth. And so adding these locust swarms, so essentially you can think of these as just like little circles that are spitting out particles. And so as these particles flow with the wind, they start branching out, similar to how a hurricane path is if you're looking at the weather. And so this gives us a somewhat crude, but it works fairly well as to forecasting where locusts will be in the next 3 hours or so. And so moving on. So one requirement for the NASA submission is that we also have to include aggregate data. So essentially data that relates to I guess population, cropland, economies, etc. Um, so I guess non-locust related data. And so here are a few overlays that we have. So this is cropland in Kenya. Um, so you can see that it's mostly there's a lot of cropland, a lot of farmland near southern Kenya. And then also you can uh, see that we have an overlay for population density. So populations are usually near the cropland, which makes sense, because people have to eat, right? Um, and so here's actually our June prediction heat map. So this is straight out of the model. So we fed the model information from a specific date in June. And this is what the model outputted as for locust risk. You know, so we actually had data on Dune already from the FAO data set and the NASA data set. So our combined data set, we already had information for Dune. So this is really just a test to see whether or not our model would be accurate in the real world. And so here's September. Um, and so we did not actually have any data on September because we were making this project in the beginning of October, right? So the FAO data set had yet to add in the new information for locust position. And so you can see that these blue-ish, purplish blobs, so the heat map is where the model actually saw there would be a locust risk in these certain areas. And I guess one other feature that we have, but we still have to, I guess, debug because it doesn't work that well, is our locust risk input box. So if you wanted to input any location on the world, all you need to do is put in their latitude, longitude, specific date, and then the website will then tell you the risk that you are at that certain location to locust one. However, I'll talk about this briefly in a few slides from now, but we have yet to actually add the model to our website, simply because of time constraints. I guess moving on from the demo, we faced a few challenges over the weekend, but probably by far the biggest challenge that we faced wasn't necessarily getting data or or executing this entire project. It was actually getting everything together and properly submitting it to NASA. Because it turns out that we almost didn't even get judged Project Locust. Um, so we made an oopsie on our end where we submitted our project to the local competition instead of the global competition. So I guess you can think of NASA space apps as two distinct competitions ish. So there are the local competitions, which are what Ping hosts. She hosts the Las Vegas one, and then the global competition. And so our team wanted to compete in the global competition. But what ended up happening was that we submitted our project to the Boston local competition because I accidentally registered our team under Boston. And so, normally this shouldn't be that big of an issue since the competitions are both fairly similar. They're both feeding towards the same, I guess, tournament. But this was an issue because it turned out Boston was operating on a different schedule than the global one. So we designed everything based off of NASA's global schedule, which is that project is due exactly at 11:59 p.m. on Sunday. But for the Boston competition, their due date was actually 12 hours before. It was at noon, and they finished judging at 5. So when we submitted our project at 10 o'clock um, that Sunday, turns out that the Boston people had already announced the winners. So they announced at 5. And so when they announced the global finalists, we were pretty disappointed that our team wasn't up there because Project Locust wasn't in the running for that. But then when we did some research as to what happened to our submission, it actually turns out that we made this oopsie. And so we instantly emailed NASA when we got word of this. It said that we made this mistake. We described everything, and fortunately enough, they saw the amount of work that we put into this project and said that okay, um, we're totally okay with judging this. And so I guess the rest is history from there. So our project got judged, submitted to the global competition, and then we were placed as a finalist for NASA. And then um, just a few months ago, NASA announced that we were winners. So we went from nothing to, I guess, being on top of the world. And so I guess this is a good example um, that life is really a roller coaster. Because if you look back on this weekend, so much has happened. There's definitely been the ups and then the downs. Because we started off the weekend with absolutely no idea what we were doing, right? And then I pulled an all-nighter, procrastinated a bit, and then I found the idea. And then we started finding data sets. And so we're all at this high point. And then when we started running into issues, we went back down to a lower excitement state. And then we went down to an all-time low when we saw that our project wasn't a global finalist. So, there are these ups and these downs in life, but all you have to do is just keep going because like a roller coaster, you can't stop. Just keep going and you'll eventually find more highs than lows. So I guess closing off this presentation, and then we can open up for Q&As. We still have a bunch of to-dos because we don't plan to stop Project Locust here. So a few things that we need to do is speeding up data acquisition because at the moment our data pipeline is extremely slow. For example, it took us 2 hours to get 200 data points, and so 200 might seem like a lot, but when talking about machine learning data sets, it's extremely small, which also played into our accuracy when training. And so in order to get more data so that our model can be more accurate, we can either rely on parallel processing, so essentially divvying up the task to multiple different processing units, or we can try and figure out a way to get a faster request time on the satellite images because it takes an extremely long time to actually ping the NASA servers and then actually getting the image, the satellite image. And so a few other things that we have to do is I touched upon this on our demo, but we actually have to connect the model to the actual site. So we have the demo on our GitHub right now if you want to look at it. It won't make much sense because it's just a bunch of characters and numbers, but we have to add that to the site, um, and then add support for the risk input box. And then a few other things that we have to do is we have to add support for additional countries because Kenya wasn't the only country that was affected by the locust swarms that happened in the summer. The locust swarms affected Eastern Africa, Southern Arabian Peninsula, and Northern India. So we have to add support for all those countries that were affected. And then maybe later on, we might add support for the entire world, having data for the entire world, and everyone can see how likely you are to get infested by locusts. So I guess that's the end of the presentation. If you guys have any questions, feel free to put that in chat. And I believe there are a few prepared questions as well.
Sonali asked, what machine learning models did you use?
So we tried initially with the simpler one. So we went with logistic regression in the initial stage, and then the decision tree, then the random forest, and then the SVM. So out of these four, the latter two worked the best.
How big is your data set? Starting which year? I couldn't find that info on your GitHub page.
So I think if I remember it right, the number of samples that we have in our data set is around 350. As Kevin already said, that we were only able to get somewhere around 200 samples for 2 hours, and we did not want to spend too much time just gathering that. So we stopped around in after 4 hours of data collection. And yeah, so and the year, there's no specific year because in FAO website, we have the data from past 30 years. So we just chose randomly so that we are not biased for any year or there's no any bias.
Colin asked, how many locust data we have for training the model?
For training the model, I think we used 80 and 20. So 80% of 350 would be 270 if I'm not wrong. Sorry if that's wrong.
He also asked, or they, what's the tool behind the demo showing the cool heat maps? How do I get it?
So it's not really a tool, but it's just plain HTML and JavaScript. And to show a map, there's a library called Leaflet. So just play around with it. It's really cool. You can either use HTML, JavaScript, or there's also a Python wrapper for it.
Yeah, cool. I'll get back to you on that because there is a JavaScript plugin that we use. I forget the name. That automatically pulls data out of Noah server. So it's very cool. I'll send you the GitHub link after.
Um, Also, what did you use for front end website?
Yeah, like as we answered previously, we used HTML, JavaScript, and CSS. They were the main things. Yeah. And to host it, I think Peter hosted it through his personal account.
Okay.
Yeah.
Out of curiosity, do you plan to patent this to avoid other people or companies stealing your idea?
Yeah, Arjun, that's a good question. At the moment we don't plan to patent it. Mostly because I guess our project was for research, for academia purposes. We could definitely patent it, but I don't have any plans on doing so. Also, this is mostly to help people, right? We don't plan to make money off of projects like this. Um, and so I'd be perfectly content with people stealing our idea because that means we're that much closer to actually helping people in Africa, or the people who are affected by the swarms. So mostly open source related for Project Locust.
Um, and how would and would you please elaborate on how you get your hex values in the dataset?
Yeah, so we get the RGB values from the pixels and then we convert them to hex. Like, is that what you're looking for?
Uh, Would you please elaborate on how you get your hex values in the dataset? That was the question.
Yeah, I mean, so we know the coordinates and the time, so we give that to the EOSTIS website that gives us back the an image, and from that we extract the RGB value, which we convert it to a hex, and then store it to a pandas data frame. Isn't that right, Kevin?
Yeah, that is correct. Yeah, and then I saw Ping just sent a question. She says that the FAO uses EU satellite data. So to be honest, I actually do not know. I don't know too much about the FAO. But the data set that we're using for Project Locust was essentially just um, presence of whether a locus is there, and then the actual coordinates and time. So we didn't have any real satellite related data, such as like
Yeah.
the overlays and the I guess the values that we used. But we only had the coordinates. So we essentially paired those two data sets together, the NASA satellite data as well as the FAO data set to get a more complete data set that we could use.
How did you plan for your project?
Um, that's a good question. How do we plan for this project? Well, I talked about this in the beginning, but everything was pretty sudden for our project because we were pretty derailed um, for the weekend. Because usually for hackathons, I usually try and start preparing like a week before, so doing research, etc., figuring out how we're going to execute this. And so we did that for this hackathon. But already said this, but all the ideas that we came up with, we didn't like. So that left us in a bit of a pickle. So not gonna lie, we didn't do that much planning per se for this hackathon. We really just we did everything over the course of 3 days essentially. But as for I guess keeping on track, we use Trello, which is a good tool as a task board. So making sure that we're hitting all the points as to what we need to get done in order to finish the project on time. And I guess Google Docs was good because we wrote up our plan and everything on that. So I guess just establishing a plan and then making sure that and divvying up the tasks into their fundamental pieces, and then essentially just finishing all those tasks in order to stay on top of it. So that was our plan, but not too good.
And also we had those regular meetings after some hours to check on the status where each member is.
Yeah. We had meetings every 3 hours in order to stay on track and to see how much we're progressing on each task.
Yeah.
Did you have the chance to do any validation, i.e., if your predictions match with actual locust outbreaks?
By validation, do you mean testing the model? Then yes, so we got a 70% accuracy, so which means that our model was right 70% of the time. And we did not have any time further to test it on any other data. Yeah.
Um, Sounds this is a good open source project to benefit the world. Is there any ideas to keep improving it to make it something that would really help people, say how to leverage government resources and encourage more people to participate?
Yeah, Colin, that's a good question. And we have a lot of plans actually. So one thing, I was talking about the data pipeline, right, and how it was extremely slow. So we hope to leverage NASA computation resources in order to speed up that process of getting data. Um, and then one other thing is that was actually oddly enough, I was looking at my news feed again, and then I saw an article about these uh, these UPenn researchers who made an app that allows people to essentially report where locusts are, like their position and their time. And so I actually plan to contact them just after this call to see if you could potentially collaborate and maybe implement Project Locust into that app. So supplying that forecasting and predicting part into their app. Yeah, there's a lot in store for this project.
Any more questions? I saw people have been using deep learning on smart farming, including insect infestation forecast. Why didn't you use deep learning?
Yes, so deep learning is kind of data hungry. And since we had only 300 samples, around 300, so it was not wise to use the deep learning as it could really highly overfit on them. Or else we should have used pre-trained models, but I don't see any pre-trained models which are used for such classification tasks. So we went on using the classical ones.
Which computer language did you use to create this project?
So mainly for this data collection, model training, we used Python, and for the website development, we use HTML, JavaScript, and CSS.
Are there pre-trained models on smart farming?
That's a nice question, but I don't think I can answer that since I don't really know. I haven't searched about it. Kevin, do you have any idea about it?
I don't have that much experience with smart farming. Um, there probably are, but there aren't any. I guess there's only one paper on anything locust related for detecting using satellite data. I mean, even what the other researchers to do, like not to put them down or anything. But they went with a different approach that didn't do everything that Project Locust was able to do. But I honestly I kind of forget what the researchers did for their paper, but it was somewhat like it was under the same topic of locusts and trying to solve the swarming issue.
Is the NASA dataset publicly available?
Yes. So, I mean, you just can't download the dataset as we have. So they only provide images for which you need to write some Python script so that you can extract patches of the satellite image of which you want. So yeah,
And then
you can
yeah,
go
and
to
then I
this
believe
website.
the majority of all like NASA data sets are publicly available. Like there probably are some like classified ones, but if you have anything like satellite related, space related, NASA probably has a data set on it, and it's probably open, which you can download and use.
I have sent a link in the channel. You
Um,
can.
How long does it take to train the data set?
This one, I think it took around 5 minutes since the samples are really low.
Yeah, so it was exponentially faster training than actually getting the data. Because it took us 2 hours to get 200 data points. Yeah, it was very quick. I was very surprised too when Yogesh told me that it only took us 5 minutes to train everything.
Some of our parents ask, what programming language would you recommend as the first programming language to learn for youth?
Yeah,
Uh,
that's a good question. What is the best programming language to learn for you? It really depends. Um, Python is said to be very open and easy to learn. So definitely if you're interested, you can learn Python. But to be honest, I wouldn't be too caught up on like what's the best language to learn. And it's like trying to figure that out. Well, um, because as long as you just like get started into programming, because if you're really into programming and if you want to become like a CS major or something, then you're not just going to stick at one language, right? You're going to probably learn a couple of languages. Um, so it's really just about starting, and then once you learn one language, then I guess you have the mindset of how a computer works and how to talk to a computer, and then from there you can start learning more languages. But I guess for people who are starting out, um, Python, and then if you're like really young, then you could use Scratch, the GUI language developed by MIT.
Besides NASA datasets in general, how do people search for datasets for machine learning purposes? Say weather related, animal related, etc.
Okay, so I think the first thing that you do is go to this website called UCI Machine Learning Repository. There they have data sets for all the research purposes, and I hope they also have the weather-related, animal-related ones. And if you don't find any there, then the second website I would suggest is go to Kaggle. And third one is really high level, but you have to search for papers which do what you do, and search for links if they have any for the data sets that they have used. And I can also paste the link of the UCI machine learning repository.
Yeah, and then not gonna lie, it's kind of hard to like I guess find NASA data sets because there's so many, and then NASA is so huge. They have all their resources spread pretty widely apart. But I guess search around on Google. If you don't find one thing, just rearrange your search, adding in more words, and then hopefully you'll find it. I guess as what Yogi just said, go to Kaggle or look on other I guess databases that have these data sets.
And yeah,
Um,
also I would like to say that all the data sets that you download from the internet might not be clean or might not be perfect. They might have nan values or zero values. So make sure you clean your data before feeding into the model, so you have the right data. Yeah.
where did you find the database you need?
Okay, so we found it from the two. We didn't find the database, but we made our own data set by getting the data from the FAO website as well as the USS NASA Worldview website. So we combined the data from these two.
Yeah, and then for the I guess for the specific components of our made data set, um, the NASA Worldview one was publicly advertised by NASA since it was a NASA event, and then said like, "Yo, you guys should use this data set when making a machine learning model." And then for the FAO data set, I believe Yogesh just searched around on the internet and found a data set from the FAO on this. So we're very lucky that we had that because if we didn't have the FAO data set, we could not have pulled this project off.
Did you follow the train, validate, test process? How did you break down the data set into train, validate, test?
So we used this method from sklearn, I guess, which is like split train while test. And I think it was 80-10-10 or 18-20. I'm not sure if we had a validation set. We only had a train and test set, if I remember it right. So what you usually do is you shuffle your data, and then you take, if this is 100% of the data, you shuffle all the rows and you take 80% for training and the 20% of the test, which the model has never seen, for testing the model, so that you have an unbiased output.
This is my first time here. Do you have step-by-step instructions and documentation of your code and processes for this project so we can catch up and understand?
Yeah, HB, I put it in chat. So we have the NASA documentation that we wrote for our project. It's fairly long. Not gonna lie, we wrote it well, operating on 3 hours of sleep. So if you find any errors or grammatical errors or something, this is probably our bad. And then for the code, we have it on our GitHub, which I also dropped. And also we have a video, which I'll send in a hot second.
And I can update the README document so that I can say which file does what, so that's easier for you to catch up on that if we have not done that already.
How large was the data set? Thousands or millions of rows?
No, it was around 350 rows. That's why we didn't use the deep learning method.
And then
SVM is good with small data sets.
Yeah, adding on to Yogesh, the FAO data set, I believe, was actually fairly large. But it took us so long to make our measly 350 data points that like we have the possibility of making the data set larger, but we just don't have the time. So yeah.
So I think there were around 30,000 data points from FAO, and we chose randomly 350 of them for us.
Can you send all these project information now via email?
Yeah, definitely. I'll send Ping all the links and stuff, and then she'll email you all.
Sure.
Are there any more questions?
Okay, if you guys have any questions on like how to win a hackathon, feel free to ask or something, or like tips for hackathons. I have a few tips. So recommendations on other hackathons. I started out competing in hackathons like 2 years ago or something. And what I did, I just started competing in like local hackathons. So, hosted by like local high schoolers, colleges, etc. Just going to those. And then I guess gradually from competing in those, I learned about these larger hackathons, like international hackathons. And then during COVID, since everything's remote, I learned about the NASA hackathon. But for specific hackathons, if you're interested in machine learning, I know Facebook, Google, Amazon, etc. They host annual hackathons, like huge hackathons, like probably 5,000 plus participants. And those are definitely hard to win since you're going up against professionals and stuff. But if you just wanted to have a good time, make a machine learning project, AI related project, those are fun. And then definitely compete in the NASA Space Apps Challenge. And then you can definitely find a few other global hackathons, like big hackathons. But if you're just getting started with hackathons or programming, definitely check out like in your local area if you have any hackathons.
And yeah, I would just like to add that this year, this NASA Hackathon 2021 is in October. So make sure that you all participate in that.
Are there suggestions to a beginner of machine learning? Say, what's the best path to get familiar with the resources of datasets, data cleaning tools, data training models, web tools, etc.?
Well, that's a good question.
Yeah.
Um, you know, Andrew Ng, the person who made Open AI, who also made Coursera, he has a really good course. He teaches at Stanford, I believe. He has a good course on introductions to machine learning. Um, Not gonna lie, I didn't complete the course because my teachers decided to give me a lot of work. But that I've heard that that's a really good course. Um, and then I guess to really learn more about machine learning, you can't really learn it in like a classroom setting. Like you can learn all the theory and stuff, but at the end of the day, you're trying to execute stuff, right? You're trying to actually make something. So what I found the best way to learn is just to get started. You know, have an idea. Like maybe you want to I don't know, like classify dogs or something. So there's a bunch of tutorials on YouTube, a bunch of tutorials on the internet about these projects. So you can just follow them, and then you can like they're guided practices basically, and you can learn about all the important parts of machine learning. And then from there you can come with your own ideas, and then just like I guess copy and paste code off of Stack Overflow, you know, and just learn from that. So yeah.
Yeah, so the best part is just to do stuff and not just watch stuff and think that you will remember it in the future. Because I did that mistake and that didn't work out. So make sure that whatever you do, even if it's copy paste, write it from your own hand so that you have that hand memory, that you know what you're gonna type and how things work. Yeah.
How do you learn machine learning and AI if you haven't learned enough math, like linear algebra or optimization?
Yeah, Ping, that's a really good question. Uh, and to be honest, it's somewhat of a struggle, right? Because, uh, like, not only for machine learning, but also if you're like handling other, I guess, like more complicated subjects, um, you need like that strong math background, right, in science, because everything is dependent on math. So, like linear algebra, calculus. So what I've been doing is really I've just been either learning it um, in uh in parallel with what I'm pursuing, right? So if I'm learning about like I don't know, um like fast Fourier transfers or something, like if you want to do like signal analysis, what I've been doing is I just like learn the necessary parts of calculus to understand Fourier transforms, and then just work from there. And then what one other thing that I've been doing is that you know it's okay to get ahead in your math because I guess there's this notion that like calculus is hard to learn, right? Calculus is for like seniors, maybe college people. But really just like pick up a textbook or look at Khan Academy. You know, Khan Academy has a bunch of tutorials and stuff on this stuff. So you can either start learning all the necessary math now, and then wait later on to actually learn all these like complicated machine learning topics, or you can learn all the math in parallel as to what concept you're trying to learn. And then Yogesh probably has a few because he's more experienced.
Yeah, so I would say that it might be a little bad idea to start learning AI without linear algebra, like the background of, because let's say in code it's really easy to fit the models and see the output. But what if it doesn't work? You wouldn't know how to debug it, or you wouldn't know how to fix it or make it better. So it's always better that you have some background in linear algebra. And for optimization, I don't think it's really necessary to have any background in optimization, but linear algebra, I would say it's really necessary. Because for optimization, you can try out using different optimizers we have. It's just a method of trial and error. Yeah.
Any more questions?